This is a summary of my paper with a very catchy title, From Hyperinsulinemia to Cancer Progression, How Diminishing Glucose Storage Capacity Can Fuel Insulin Resistance. Say that 3 times fast. Okay, so the motivation for this particular project was actually a very cool experiment that was conducted in 2018, or at least published in 2018 by Hopkins et al. What they did is they gave mouse or a bunch of mice a tumor. They treated them with PI3K inhibitors, saw a response, that was great. But one of the consequences of using this particular medication due to just its mechanism of action is at least transient elevation of glucose and insulin. Well, unfortunately, insulin actually can feed the tumor, so they saw tumor regrowth. And then to deal with that, instead of trying different medication, they actually treated mice for this transient diabetes. And they tried different interventions like metformin, SGLT2s, and keto diet. They managed to normalize the blood sugar and particularly insulin, and boom, the response was restored. So this was really interesting to me. It looks like, okay, PI3K inhibitors cause transient diabetic phenotype, and correcting that restored response to the drug. And amazingly, it worked in all 12 cell lines they tried, including breast, lung, pancreatic cancer. And I look at this, and why this was particularly interesting to me is that it looks like an example of non-genetic resistance, so the way that I think about it as non-genetic resistance. And here, particularly, something was triggered by the drug that was actually unrelated to its mechanism of action, but that's what resulted in a loss of efficacy. And reversing this adaptation actually allowed resensitization to this particular therapy. So it's in contrast to our very familiar genetic resistance. When you kill off all the sensitive cells, what you have left are the resistant cells. But here, it is the change in the environment and the more systemic response that caused loss of efficacy, and correcting that more systemic response actually allowed resensitization. So I thought this was really interesting, and I wanted to describe this experiment mathematically, because that's what I do. But for that, I needed to actually describe this emergence of hyperinsulinemia and hyperglycemia, so essentially describe emergence of type 2 diabetes. And for that, I needed to understand the emergence of hyperinsulinemia and hyperglycemia and essentially emergence of type 2 diabetes. And that led me down the rabbit hole to oral glucose tolerance tests and the Kraft patterns. So what are those? Well, as an interesting thing, that I found out working on this project, hyperinsulinemia actually precedes elevated blood glucose, and what is much more important, is often undetected. One of the classic studies where they really observed it was this Kraft et al. In 1975, and then it was updated by Crofts et al. In 2016, and they analyzed the response of thousands of patients to an oral glucose tolerance test. So what is that? So you fast for some time, like I think usually 8 to 12 hours before the test. So you are at your fasting glucose and insulin levels. Then you drink a disgusting liquid with 75 milligrams of glucose. Sometimes it's 50, sometimes it's 150, but it is a standardized glucola drink. And then a vampire measures your blood glucose and insulin levels at 0, 30, 60, and 120 minutes. Sometimes they do it for longer, but I mean, it is drawing your blood every half an hour. It is highly unpleasant. So, but these things are done for understanding the glucose-insulin dynamics, or also when testing for gestational diabetes. So half of the world population should be familiar with this. And they identified, so what they did, they identified these 5 key patterns of glucose-insulin dynamics. So yeah, these are the references that you can follow up on. And the 5 patterns were as follows. So the pattern 1 is when fasting insulin levels are kind of below 30 international units per liter, with a peak at around 30 to 60 minutes after ingesting glucola, and everything returns to baseline by about 180 minutes. Pattern 2, so the glucose dynamics was absolutely also normal, goes up, goes down as expected, but the delay, the return to baseline of insulin was actually delayed. Interesting. So then pattern 3 was when the peak of insulin was more delayed. You had higher postprandial glucose levels, so higher post-meal glucose levels, and it took longer to return to baseline. So these first two, I mean, these are not the best figures, but they are from the source over here. But you can see, okay, so the peaks, especially this green line, the insulin are getting delayed and delayed and more delayed, and also the absolute peaks will be higher. And then pattern 4 was this, so you had elevated postprandial levels of glucose, longer return to baseline, and higher baseline levels of both insulin and glucose, which is really much more consistent with type 2 diabetes. And again, you can see just how these things are starting to, the peaks, the time that it takes to go back to baseline, and also actual baseline is higher. There was also pattern 5 where insulin levels never rose and blood glucose levels were very high, but that's more of type 1 diabetes. That's a separate beast in its own. So we're really going to be focusing on these first 4, which are much more consistent with emergence of type 2 diabetes. Okay, so that seems to be the thing that I need to try to figure out how to describe. And going back to insulin resistance paradigm, and of course the classic paradigm that I learned and everybody else initially did, is the lock and key paradigm. And that insulin works like a key, so the cell is kind of like here, and you have these locks on the cell, so the insulin receptors. When the insulin molecule binds to the receptor, it opens this channel over here and the glucose can go in. And then problems arise supposedly when maybe you do not have, maybe the locks are jammed or gummed up, and so the key cannot turn. So these the channels maybe do not open to let the glucose in. I mean, that's at least the classical paradigm of understanding of emergence of insulin resistance through loss of sensitivity to signaling. Well, the more I'm reading about it and the more I've been thinking about it, it doesn't seem like maybe that is at least the entire story. And maybe a better analogy would be that of a full train car. This is just found a random picture from, I think it's Metro in Japan, where you actually have guards pushing people into these overstuffed train cars. And the analogy here is that if the train car is full, opening more doors or keeping them open longer will actually not let more people enter until some have exited. And if you think about these doors being your channels, the glucose transporters, and this being your glucose and these being your cells, well, you can keep opening all the doors that you want, but unless you empty the cars, more glucose cannot fit in. So the idea is that maybe the cells are full or at some kind of a capacity. And within this framework, of course, then the cause of elevated blood glucose is not just the inability to open these doors, but also the lack of capacity of the cell to actually store any additional glucose. Okay, interesting. So we're kind of getting closer to formulating the model. And then there are 3 really interesting key experiments that I would like to share before I present kind of the framework that I ended up with. So this was a very interesting experiment by Gavrilova and co-authors from 2000. And what they did is they took mice that have no fat and who had elevated blood glucose. And then they surgically implanted adipose tissue into them. That essentially created a glucose storage depot, so added more train cars in there, which sucked up excess glucose. So glucose went down, top panel is glucose, and then insulin then went down as well, because you do not need to try to keep pushing the glucose inside the cells anymore. They are now nicely packed away, and even the weight was kind of normalized over here. So that was really interesting. So this idea of carrying capacity and limited carrying capacity, and also adding capacity to store glucose, was really shown in a very cool way here. Another experiment is about insulin and lipolysis, so the ability to break down fat, and more specifically in this particular case, so releasing excess glucose from adipose tissue from storage. And here they were showing, so this is 1989 paper, that essentially you have, when you have really high insulin concentration, the fat breakdown slows down. So effectively, it traps the fat and the glucose inside the cells, which of course now creates this feedback loop, because if the glucose is high, insulin is high, well, then insulin cannot go down until glucose goes down. Anyway, you end up being trapped in this. So that was really interesting. And then another experiment that was also really important was from Afanova and colleagues as well from 1998. And that one showed that high glucose can actually be toxic to beta cells, which obviously produce insulin after a point. So they showed that, okay, if you have like the glucose concentration, and I guess they co-incubated cells with them, and like that there exists this sweet spot around maybe normal glucose concentration. I'm assuming it might be different for different people in this range, but approximately here, and that before or after, if glucose is too low or glucose is too high, actually beta cells start to get damaged. And of course, if you damage enough of them, then they will not be able to produce insulin, and maybe you can even result in type 1 diabetes. But the important aspect here is that there is this window of optimal glucose concentration. Interesting. Okay, so let's kind of summarize the key mechanisms of what happens when food is ingested before you can try to build a framework to reproduce these craft patterns. So, okay, food is ingested, so blood glucose goes up, then insulin goes up because it needs to pack it away into cells. When glucose is cleared to homeostatic levels, then insulin also returns to baseline. Okay, great, kind of what we know. Glucose clearance can be both insulin dependent and insulin independent. So that was pretty interesting. Like GLUT1 transporters, for example, they line the blood-brain barrier to prioritize glucose distribution into the brain without it having to regulate it with another hormone. That was kind of interesting. So usually right now when we're talking about glucose clearance, insulin-dependent clearance would be with like transporters like GLUT4. Glucose can be stored in 3 main compartments, in the liver, in the skeletal muscle, and in the adipose tissue. Skeletal muscle is the largest kind of storage depot, and we're going to come back to that later. And one of the big model assumptions that was introduced here, based on especially that very interesting experiment from 2000, is that there exists glucose storage capacity. And if it is full, then glucose levels in the blood remain high. So essentially capturing this framework over here. And as I mentioned before, also lipolysis is inversely proportional to systemic insulin. So capturing this here, if insulin is high, then lipolysis is low, and vice versa. And then high insulin means that glucose is not really released from the cell, so it cannot make room in the carrying capacity. Train car remains full. A little bit of a trap here. Okay, so can we now understand and describe emergence of insulin resistance within this updated framework? I was working from some classical models, starting with the one by Bergman from 1979. Then there was this very cool update by Top et al. From 2000. Let's go through them. Okay, so we have food. Food gets absorbed, so basically like adding a bolus, that somehow gets into systemic glucose. Then there's also gluconeogenesis, so the body always produces glucose from the liver to maintain homeostatic levels, so we do not die. This term here is to reflect that gluconeogenesis is actually decreasing if you have really high insulin, which makes sense. It's a signal saying that, okay, there's enough. Insulin is high means that there is enough systemic glucose that maybe we do not need to keep pumping it out from the liver. And then when it goes back to baseline, then the production term becomes larger again. a simple term for insulin-independent glucose clearance, and then this main term, which is insulin-dependent glucose absorption into the cells. So this SGI, S would be like sensitivity, G glucose, I insulin. That is more or less standard term. So really the main change here is addition of this carrying capacity, and that it is getting absorbed into. So GC is glucose in the cells up to carrying capacity K. Okay. As I said, this is a really new term. Insulin term, this is really from these existing models. So this beta cell dependent production, this is a funky term. Please look at Top et al. For a very cool description. And it was parameterized, so these powers were parameterized based on very interesting experiments. And of course, there must be some kind of a clearance rate. Beta cells, again, this is glucose-dependent production with glucotoxicity, the top models, and also Uri Alan did very interesting updates to this, but this is the same structure. The idea that there exists this sweet spot for insulin production in beta cells. And then finally, the intracellular glucose. This term, again, here is... So here it came from the blood into the intracellular space. And this is the term that came up with to describe insulin-restricted lipolysis. So this is also a key new term in this model, this one and this one, showing that lipolysis is inversely proportional to systemic insulin. And that's going to make a difference in the ability to capture the Kraft patterns. Okay, so Kraft patterns. This is the model. And my goal here is to describe the emergence of Kraft patterns. So I want to see if what I can do in order to simulate the norm, and then Kraft, so 2 pattern, Kraft 3, and then Kraft 4. I'm not focusing on Kraft 5 because that is type 1 diabetes. That's a different story here. And the hypothesis is that reduction of carrying capacity, K, is sufficient to reproduce the key features here. I mean, intellectually, if you just think about it as a thought experiment, that would make sense, that you will just be stuffing your cells more and more, and so that will cause these delays in the ability to clear things. But we still need to show it. Okay, so reproducing Kraft patterns by varying glucose storage capacity. The approach here is to reduce, as I said, carrying capacity K. So right now I'm just reducing the parameter value and record the predicted glucose and insulin patterns. And I want to capture essentially this. Okay, so starting with like K equals 50, these are normalized to something. I do not have real values, obviously, for these. So I'm trying to think in terms of maybe it's a percentage. So I've been working in the range from 0 to 100. Whatever that may be. These also, again, cannot really digitize these data very well, but at least gives a sense of approximately the ranges of these, where these variables should be, and also approximate timing of when the peaks should be taking place. So for the purposes of this particular modeling exercise, this is sufficient. Okay, starting with K equals 50, so we have plenty of room in the carrying capacity. Glucose goes up and then goes down, so insulin follows. This goes down, and they kind of eventually equilibrate. So this is simulating a meal, essentially, like an oral glucose tolerance test, and what's going to happen after. Okay, now I'm physically just reducing the value of that parameter to, say, 10. So glucose looks approximately the same. Maybe the baseline is a little higher, but very much still within the norm. Insulin also, okay, so this peak is maybe happening a little bit later than this one. And the baseline insulin, where we're ending, is also going to be a little bit higher in this particular simulation. So we keep squeezing the carrying capacity. Okay, now if you see, you can even just visually see that this is taking longer. So you're having more of a delay in returning to norm of the glucose. And of course, the peaks of insulin are higher and they happen later. And the baselines where we end up are also keep getting higher and higher. And now we're starting to be in the maybe pre-diabetes territory. And then finally, I'm just making it really, really small for illustration purposes. Supposedly, essentially type 2 diabetes. And okay, so these go really high and then kind of go up and equilibrate at the really pretty high level. And once again, the delay in insulin, so it happens later and it is higher and the baseline is higher. So generally, it seems like we are able to at least capture the qualitative properties of these patterns and the transition, the gradual transition from one to the other by just reducing the carrying capacity. So that's interesting. So that was for oral glucose tolerance test. Now a little bit more, maybe longer term fasting glucose trends. So right now what I want to ask is about, okay, so if you are reducing the carrying capacity to store glucose, what's going to happen in the long term to fasting glucose and insulin levels? And essentially I'm running simulations to steady state for varied values of parameter K, record equilibrium levels of insulin and glucose, and plot them. So on the x-axis here, for example, I have the carrying capacity K as I am reducing it. So starting from 100, percent, and then reducing it lower. And then I'm recording the average fasting glucose here. So kind of normal range, pre-diabetes range, and diabetes range. And the same thing for insulin. Interestingly, finding the exact kind of cutoffs for insulin or any kind of correspondence with what is a pre-diabetic insulin range is not really a thing that I saw in the literature. So I'm just kind of putting it so below 25 versus maybe above 25. This seems to be somewhat consistent, maybe 30. Okay, so what do we see? We see that decreasing this carrying capacity starts to impact, like really impact baseline only when you're about the 15 to 20% of capacity to store glucose. While these are not exactly real numbers, I do not have much data to parameterize it on, but still, conceptually, interesting. And also it suggests that maybe there exists kind of quite a bit of a buffer or like a range of this carrying capacity that still allows you to maintain normal levels of glucose and insulin, even as the capacity to store glucose decreases. So that's interesting, especially when we start talking about what does this capacity actually mean. But before we get to that and some other fun things, let's talk about impact of insulin sensitivity. I mean, yes, reduction of carrying capacity, of course, will be important, but insulin sensitivity is probably also like the ability, this lock and key thing, probably still is very important. So if you're looking at this term, it's this, I was looking at just the K, but now I also want to look at the S. Again, you can just see from the equation, obviously it's going to affect this, how quickly or slowly it goes from here to over here. So similar graph, although now in, I guess, more dimensions. So on the x-axis, I have the K, my carrying capacity. On the y-axis, I have this parameter S, this insulin sensitivity. This is a plot for fasting glucose, and I'm generally indicating, so this is the average glucose, fasting glucose that we're predicting, kind of normal range, pre-diabetes range, and then this is now getting to be more in diabetes range. And same thing for the fasting insulin. Again, kind of norm versus elevated. So, okay, I mean, you can see that obviously high capacity to store glucose can, to an extent, actually compensate for low insulin sensitivity. If you have a really high K, but you can actually have a normal carrying capacity, even you have a really kind of a smaller S here and here as well. But if you are at the lower end of this, like reduction of the capacity to store glucose can maybe potentially lead to accelerated development of this phenotype if you also have this low value of S. Okay, that again intuitively makes sense, but very helpful to see. And now, just because this whole thing started with me trying to understand and describe the results of the Hopkins experiment, so back to cancer. What they did show in that experiment is it was really driven by insulin. Like they normalized glucose, but not until they normalized insulin did they start actually seeing improvement in responses. And so I want to assess the impact of underlying hyperinsulinemia on cancer progression. So what I do, I introduce an equation for insulin-augmented tumor growth, and I'm going to simulate how my simulated tumor will grow in different Kraft environments. That is, my simulated tumor is going to grow in a person who is simulated person with a Kraft 1 pattern of OGTT versus Kraft 4 pattern. The equation is relatively straightforward. So you have a positive term, the growth term, so some growth rate, proportional to current tumor size, proportional to insulin, and proportional to glucose. So if you have more glucose, this will be bigger, but if you also have more insulin, this will be bigger. So intuitively, again, you can already predict what's going to happen, but still nice to see, and some death term. So this is the glucose simulation of my different Kraft patterns. I'm just doing my OJDT simulation, but still, obviously you can extend it to any simulation of meals, any simulation of other things. So we have here, again, from Kraft 1 at the bottom, obviously, because it would be the lowest baseline glucose level, Kraft 2, 3, 4. And same thing for insulin, again, all expected. Now let's look at our simulated tumor. So in the Kraft 1, the blue one, and to an extent to Kraft 2, clearly the cumulative effect of this G and I, so this glucose and insulin, is not enough to make this term greater than some natural death term. So even if my simulated tumor appears, the environment is not permissive for it to grow. So especially here, it's still just going to disappear and going to disappear. But if we have Kraft 3 or 4, that's what we have here. Okay, my microscopic tumor might be now in a permissive enough environment to actually start growing. Yeah. So this term is going to be bigger than this term, and then it's going to grow. So the key result here is that underlying hyperinsulinemia, even with normal blood glucose levels, can impact the difference between cancer progression and regression. Again, if you think about it, if you think about insulin as fuel and fire, that makes perfect sense. But putting all of these pieces together, and especially thinking about the fact that hyperinsulinemia happens before you notice high glucose. So you might not know that this is happening, but the environment might already be permissive. And then I just did this, again, longer term simulation, and here I wanted to look at simulating the impact of these parameters S and K again on the dynamics of the simulated emergent tumor. And the question is, would it essentially progress or regress? So I will vary the values of K, I will vary the values of S, and then run my simulation for however long, and then record, is the final simulated tumor volume smaller or greater than what we started with? And that is what we have. And again, same thing as before, and makes perfect sense, but good to see as well that with high carrying capacity, with high capacity to store glucose, there is a lot of room for this here, even if you have low insulin sensitivity. But at some point here around, I guess, 10-ish, well, this stops compensating for it. And now we're ending up in the world of tumor progression. And parameter S is most likely genetic, but parameter K is not. Again, I'm going to get to that shortly. I guess to summarize, again, the key results. So when insulin sensitivity is low, should a tumor appear, it is more likely to progress, even for large glucose storage capacity. So if it is really, really that small, I guess this does not seem to compensate in this simulation. This is a simulation, but this is really to show the qualitative patterns of what we can expect. And for individuals with higher insulin sensitivity, well, then you can actually be a little bit more protected here, theoretically. Can prevent an emergent tumor from progressing. Okay, so reduction in capacity to store glucose can over time create a more permissive environment for tumor progression. So here, as before, as I said, I was just mostly fixing my value of K and then simulating things. But here I wanted to try something different and actually have a decline in K over time. So this is again simulation for however long this is. This is really to illustrate the point. So if your K, the capacity to store glucose, declines over time, then maybe you might create eventually or get to a state of an environment where this might be still under control, maybe a type of dormancy, I don't know. But at some point when enough of fasting glucose went high enough, fasting insulin went high enough, and that was enough to tip the scales for this positive tumor growth term to be greater than the death term. And then same situation, but we went from regression to progression. Well, that would be unfortunate. So to summarize, kind of the main point that I was really looking to make here about cancer and type 2 diabetes. We do know that type 2 diabetes is linked to worse cancer prognosis. It does seem that patients with pre-existing type 2 diabetes have poor outcomes across many cancer types. But it doesn't seem like maybe there's higher incidence, which is interesting. And this really describes a relatively simple mechanistic framework for why that could be. I don't know if you remember, there was this paper from a few years ago about how cancer's emergence or appearance is essentially bad luck. And I mean, carcinogens and all of those things aside, I think there's a lot to it. And if you have this spontaneous tumor, then it needs to be in a permissive enough environment to grow. And maybe people with higher hyperinsulinemia or pre-existing hyperinsulinemia, which is, as I said, sometimes hidden because it happens before high glucose, maybe that is one of the things that creates a more pervasive environment. And so hyperinsulinemia may actually be a hidden driver, because insulin acts as a potent growth factor for many tumors. A lot of people say you might not be able to get cancer cells to grow easily in a petri dish, just add some insulin and they blossom. And also in this paper, they showed that it was reversing insulin elevation, like they were looking specifically at insulin that restored therapy efficacy. But of course, you can't have low glucose without low insulin, because insulin follows glucose, but you can have low normal glucose and high this hidden insulin in other craft patterns. So something to really figure out how to monitor maybe sooner. And kind of droning in on this point, normoglycemic does not necessarily mean somebody is metabolically healthy. Like there was this, again, this Crofts paper, over 50% of people with normal oral glucose tolerance tests show actually elevated insulin responses. So it's just kind of hiding there. And maybe these individuals are primed for tumor progression despite appearing metabolically healthy. Something to keep you up at night. Okay, so now not all glucose storage is created equal. Going back to this point of where does glucose go? As three main places where it can go. Excess glucose can, of course, go into fat cells, into adipose tissue. And maybe some people genetically have more expandable fat depots. Somebody is able to create more of these spaces and essentially store more excess glucose as adipose tissue, but it doesn't spill out and does not cause hyperglycemia. And maybe somebody else may reach their storage cap early, even at normal BMI. There could be not lean individuals in Asia is what it's supposed to say. Like there are a lot of people of Asian descent sometimes have lower capacity just to store glucose, and so it spills out sooner. Of course, then the other one is the liver, and the overflow glucose can lead to fat accumulation, can lead to NAFLD, which is now, and then to NASH, which is now called MASLD. Prevalence, like pretty high prevalence, about 25% people in the US when I was last looking. But it is very reversible when treated early. Again, the idea is to drain it out, let it actually come out of the liver. But so it is very reversible, but if not, it can lead to cirrhosis, and that is a very bad thing. But the main largest modifiable reservoir of glucose storage is the skeletal muscle. And it's a wonderful thing because storage capacity can increase with training, but it is also lost through inactivity, with age, with bed rest. I'm going to get back to that one shortly. And this is the one I really want to kind of talk a little bit more about, because this is the one where actually one can make a lot of difference. So skeletal muscle, it accounts for truly the majority of insulin-mediated glucose uptake, and it does decline, yes, we know, with aging, with sedentary lifestyle, with illness, with injury, or bed rest, but it doesn't actually do it just linearly. And this is a very interesting point here. So exists this notion called catabolic crisis model. And it states that the decrease in movement during recovery from injury actually causes age-related muscle loss to accelerate. So if you look at it, what you would think is happening is like, oh, we are just all losing muscle here. But if you zoom in at what might be actually happening, oh, like somebody here fell or had to recover from a surgery, they were on bed rest. Muscle is the first thing to go because maintaining muscle is very metabolically healthy, metabolically expensive. Okay, so maybe built up a little bit more. Oh, had another injury, or maybe had incomplete recovery, or maybe was moving a little bit less. And so you actually have these discrete events, but the consequence of them is you do not rebuild the muscle mass back to whatever your baseline was. And so you're always like chipping away a little bit more, but it's not a natural, just gradual thing that happens. Maybe is driven by lots of these discrete events. Another super interesting thing that I found is that muscle also enables insulin-independent glucose clearance through like GLUT1 transporters. And actually, apparently, some diabetes patients can manage, like mostly type 1, can manage blood glucose with less insulin through exercise because the muscles actually take up more excess glucose. So that was just really interesting. Now I'm just going to go through questions that were thrown at me by the reviewers, and I just want to discuss like different points that have come up whenever I talk or think about this, like pharmacological intervention. So what about metformin? I mean, people have been trying metformin as, for example, cancer combination agent, and I mean, it's not really working. Why? Well, the mechanism of action of metformin, the way that I understand it, is it affects the hepatic gluconeogenesis. That is, it reduces the amount of glucose that your liver just pumps out at baseline. And it seems like, from my at least survey of the literature, that the impact of insulin on insulin is actually inconsistent. Even in this paper, they showed that metformin was the least effective one, like it's basically the same as the vehicle, so it didn't really have much of an effect here. And it kind of makes sense because also if you look at blood glucose here, like the normal chow and the metformin, they're all about the same. And if glucose is high, that means insulin is high because insulin follows glucose. And the clinical results that I've been seeing also mixed results as kind of cancer therapy complement. But in a world like this is the case, and if it is indeed insulin that is actually acting as growth factor in tumor cells, well, if you do not reduce the insulin, why should it be working? So it's probably due to mixed impact on insulin, not glucose alone. So lowering glucose without actually lowering insulin might not mitigate these cancer promoting signals. So in the last 10 years, we really saw a big change in how we think about treating diabetes, type 2 diabetes, and about the medication types. Before it was just trying to give more insulin, but now there are different classes of therapies. Of course, everybody knows about the Ozempic, the GLP-1s, but I'm really excited about this GLT-2s. So these drugs, they essentially they block the reabsorption of glucose into the kidneys, so extra glucose does not go back into systemic circulation, and you pee it out before it actually makes it into the circulation. Very effective things. And then there was this very interesting study from 2023 by Lo et al., and they looked at almost 25,000 patients with non-small cell lung cancer with pre-existing type 2 diabetes, and they showed that these people who were on SGLT2 inhibitors for over 12 months, so they actually had time for medication to start working, exhibited a very, very significant reduction on all-cause mortality compared to non-users. Yes, as I said, they lower blood glucose by blocking reabsorption into the kidneys. So, potential mechanisms. I mean, very likely it is, or at least definitely should be within this paradigm working, is lowering glucose and insulin, so less favorable environment for tumor growth. So basically this positive term of my tumor growth equations is getting a little smaller, and then by adding extra negative terms, extra kill terms, not only through natural death, but also through other probably cytotoxic therapies, would then lead to tumor regression. Okay. And also, maybe there is some direct tumor impact. I saw some things on SGLT2 expression, maybe has been observed in some other cancer cell lines. So inhibitors might actually directly affect tumor metabolism and also indirectly affect the environment. So that was really, really interesting. This is a retrospective study. It's not that they put healthy people on SGLT2, well, healthy, otherwise metabolically healthy cancer patients on SGLT2s. It was people who had type 2 diabetes, were on these medications, and then developed cancer. So they actually seem to be doing better. Interesting. This one was kind of interesting, also very recent experiment that I liked. So if you remember the classic experiment that I mentioned before by Gavrilova et al., that where they transplanted healthy fat tissue into fat-free mice. And as a result, they normalized glucose insulin and reverse diabetes by creating this glucose storage depot. So this was a result. Well, I just saw this study that came out very, very recently, where essentially they did, looks like something very similar. So these engineered adipocytes were implanted into tumor-bearing mice. And as a result, of course, blood glucose and insulin went down, as we now know, because they got sucked up into these newly created storage depots, and that seems to have slowed tumor growth. So it's mechanistically the same idea, create a storage depot for excess glucose, but I guess approaching it from different directions, rediscovering it. So I thought that was pretty interesting. Another question that has been coming up is on ketogenic diet. I mean, yes, the Hopkins experiment did show that keto diet was actually extremely effective for these particular animals. That being said, the rodents, they're not humans. Maybe some other things are happening there. So keto diet, everybody probably knows, but just a review, high fat, low carbohydrate diet. And actually, therapeutically, it was, and probably, as far as I know, maybe still sometimes used for epilepsy in 1920s. They started it and still do. Seems to be helping with childhood epilepsy. What it does is it induces ketosis, so the body shifts from glucose to ketone bodies like beta hydroxybutyrate for energy. Okay, so what are some preclinical and clinical studies that I found? Preclinically, so there were mouse models, as I said, where it has been shown to slow tumor growth, like in the Hopkins, so that worked there very well. There was another study showing that maybe it enhances CAR T cell function, improving tumor control, like that was lymphoma models. But also I found this paper from 2024 that it's implicated in promoting metastases. So I don't know, not very clean. And again, are they looking at, for example, if you have, I don't know, hyperinsulinemia, but also feed them beta hydroxybutyrate? Would that actually lead to, can you have it on a keto diet? I'm not familiar enough to really make a judgment here. Just sharing the information on this. In terms of clinical observations, as far as I know, the results, the human studies are limited and heterogeneous. Some suggest benefits, some do not. It's pretty certain that AML, they were actually shown to accelerate disease progression. So maybe because more fatty acids and AML cells maybe are actually liking it more than regular glucose. Don't know, but this was a study that was shown there. And some studies in breast cancer show that a keto diet might be helping. But again, results are inconsistent. It's very unclear what is exactly the mechanism of action. Is it the systemic nutrient environment? Is it the beta hydroxybutyrate? Is it something else? Not entirely sure. So to kind of summarize, just really some of the final thoughts here. So which anti-diabetic drugs could help manage insulin and by extension maybe could be interesting combination partners for cancer therapy? So these things that I don't think I can pronounce, but their mechanism of action is they stimulate pancreatic insulin secretion. So the idea is that maybe for people who just do not produce enough insulin, or when we were still in a world where we thought that the only way to manage diabetes is to increase insulin, to kind of push more glucose inside the cells. So these drugs, they stimulate pancreatic insulin secretion. Yes, so it obviously increases insulin, so probably not great for cancer. Metformin, as I mentioned, so mechanism of action here seems to be decreased hepatic gluconeogenesis, and effects on insulin are mixed, which kind of also maybe makes sense if other factors are taken into account. If somebody then also watches their diet a lot, then maybe that will give a little extra boost. But literature suggests that there are different cases and it's not very consistent in reducing insulin. But also insulin is not something that's really being tracked as much as glucose. And of course, the SGLT2 inhibitors, they seem to be very promising based on that study that I shared by Lu et al. From 2023. So interesting. I did not find many things on GLP-1s, so the Ozempics, Wegovys, semaglutides, Mounjaros, all of those things in cancer. So theoretically, if it is acting on this mechanism, then it's a good thing. That being said, what are the off-site effects? Is there something else that could be happening? I do not know, so I didn't see that. So I'm not putting that on the list. Final slide that I just wanted to share because we live in a cool time of wearable technology. Continuous glucose monitors. And these are small sensors, so they get inserted into subcutaneous tissue. Usually people just put them on their arms. And they measure interstitial glucose levels every few minutes. So the glucose levels basically between your cells, which is a proxy for your systemic blood glucose levels. And they give you dynamic insight and maybe postprandial spikes, like how your body reacts to different foods. Different people will have different reactions even to the same foods. And this is one of the devices that really helps fine-tune and tailor one person's individual responses to individual foods. Maybe craft-like behavior during the day, at least with respect to glucose specifically. Sleep patterns like dawn effect and all of these things. So these are very interesting things. And they're widely used for type 1 and type 2 diabetes patients for blood sugar management. And they really seem to be quite remarkable for that. But they don't give the full picture because they do not track insulin. Because insulin is a protein, not a small molecule like glucose. So you cannot measure its concentration with a small sensor in the space between your cells. It requires antibody-based detection like ELISA assays. And to my knowledge, not yet miniaturized into wearable sensors, but would be really, really cool. So measurement of insulin specifically is still very episodic, not continuous. To my knowledge, really only like any dynamic patterns are really only measured during oral glucose tolerance tests, or you get just snapshot measurements whenever you get a blood draw. But still, would be very cool if one day, hopefully soon, somebody figures out how to do ELISA on a chip. Okay, so this is the paper with a short and catchy title. Came out, I guess, last year. This is my personal work, personal research and interests. My personal views do not necessarily represent the views of my employer. And no financial support was received, not supported by big, I don't know, SGLT2 or something. I just think these are very interesting mechanisms and things to think about. And that is it. Thank you.